Let's discuss what we mean when we talk about the bandwidth of an oscilloscope. We often refer to bandwidth in the name, such as a 100 MHz oscilloscope. The bandwidth of a scope is more correctly called the -3 dB bandwidth. When a signal at this frequency is input to the instrument, the scope's reading would show 3 dB less than the actual signal on the input. A scope's traditional frequency response curve looks something like this. Here we mark the -3 dB point with a blue arrow. As you can see, the frequency response varies within the scope's operating range, but once the -3 dB point is hit, it will generally fall off quickly. Here we can see what amplitude different frequencies appear as, even though they are all the same actual amplitude. So the amplitude of the signal will vary by frequency, and this is included in the scope's specifications. But this is not the only way that the bandwidth affects a signal. Bandwidth also affects the rise time of a signal. Rise time equals about 0.35 divided by the bandwidth. The rise time of a measurement is the square root of the sum of the rise time of the scope squared plus the rise time of the signal squared. To show this effect, we can look at a 50 MHz pulse on a 100 MHz and 500 MHz oscilloscope. First, let's look at the 100 MHz oscilloscope. This is showing a rise time for our pulse of about 4.4 nanoseconds. Now we can compare that with the 500 MHz scope. For the same signal, it's showing a rise time of about 3.3 nanoseconds. Because the higher speed scope gives more weight to the higher frequency components of the pulse, the rise time appears faster. The math indicates that having a 5x the bandwidth of the frequency you are analyzing limits your rise time error to about 2%. This is a good rule of thumb. Bandwidth is an important consideration in the error budget for your scope measurements. It impacts both amplitude and rise time. Use the 5x rule to keep your rise time error to about 2% as a best practice in signal analysis.